Hi everybody, this is Indira, Assistant Professor of Institute of Aeronautical Engineering, Department of Mathematics. Today we are going to see the next topic of matrices and calculus, that is triple integrals. It comes under the fifth unit, multiple integrals. Already we have seen in the last two sessions how to solve double integration and change of order of integration and double integration in both Cartesian and polar. Today we are going to see how to solve triple integral in Cartesian coordinates. So before going to solve the triple integrals, let me introduce what is a triple integral. Recognize where to use this triple integration. Triple integration, when we are doing triple integrals, we need to recognize when a function of three variables is integral over rectangular box. Evaluate a triple integral by expressing it as iterated integrals. Recognize when a function of three variables is integrable over a closed or bounded region. And simplify a calculation by change of order of integration of triple integrals and calculate the average value of the three variables. Now, what is the definition of triple integrals? A triple integral is an iterated integral with three variables and over three-dimensional region. We can treat triple integrals definition as the extension of that of the double integrals, but this time we are integrating over a volume instead of area. Triple integral, what to do triple integral represents? What do triple integral represents? Triple integral is used to find area under a curve. A triple integral is used to find volume of three-dimensional object in 3D space. The triple integral is used for functions of three variables. If D is closed region in a space, the total volume of the region can be written as triple integral of D over D, and which is equal to triple integral of D into dx, dy, dz. And this is used to find out the volume of the given integrals. Hence, the meaning of the triple integral is explained. If x1, x2 are the constants and y1 and y2 are the functions of x and z1 and z2 are the functions of x and y, then f of x, y, z is first integrated with z between z1 and z2 and keeping x and y keeping y and z as fixed. That means that while doing the triple integrals, when the limits are given for x, y, and z, then the internal first integral is done first, then the y, then x. If all the three, there is a two choices will be there, where all the three variables are maybe constants. If that is the case, if all the three limits of x, y, z are given as constants, then simply you need to follow the order that is 1, 2, 3. That means first the internal integral, the inside integral is done first, and then 2, then 3. Suppose, I'll give an example. Suppose that integral of x, y, z, triple integral of x, y, z, and z is equal to 1 to 2, and the next is y is equal to 4 to 5, and suppose that x is equal to 0 to 1. If this is a given equation, then we need to do all the three are independent with each other, and z can be done first because it is a first integral, and then y, and then x. Let's suppose that if you have an integral like y is equal to 0 to x, and x raises from 1 to z, and z raises from 0 to 1. If such is a case, then we have to do the y integral first. Whatever may be the order here, first we need to do y, because the y is first converted into the x variable, then the x variable is converted into the z variable, and the z variable is converted into the constant, giving the numerical answer for this triple integral. So this is how the triple integral order as can be followed. Now, let us take one example of how to solve a triple integration. Here, evaluate integral of 0 to 1, 0 to root of 1 minus x square, and 0 to root of 1 minus x square minus y square, x, y, z, dx, dy, dz. That's the question. Now, in order to do this triple integral, first we need to see the variable limits that are given here. The variable limits here, it is a function of f of x comma y. That means these are the values of z. So the integral for z is done first. Then the triple integral is converted to double integrals. And the next, the limits are now from x, y, z, from the function of x, y, z, z is almost, it is eliminated after converting this. Then the remaining in x and y, you can see to which variable, the variables are in terms of x. That means that these are the limits of y. That is y raises from 0 to root over 1 minus x square. Then the last one, that means even this y variable is also can be cancelled, is also eliminated, and remaining only one variable, that is x. That means the last constant limits are there for x 0 to 1. So let us see how to solve this. Look here. Integral of 0 to 1 dx, integral of y to root over 1 minus x square dy, integral of z raises from 0 to root of 1 minus x square minus y square, x, y, z into dz. Now, here we are doing with z. So, integral of z is nothing but z square by 2. Z square by 2 upon the limits z is equal to 0 to under root of 1 minus x square minus y square. Now wherever z is there, you can replace this. You can replace this value, that is upper limit. That is nothing but, you can see in the next slide, that is 1 minus x square. 1 minus z square is replaced by z is nothing but under root over 1 minus x square minus y square. So z square is nothing but 1 minus x square minus y square minus 0 square, and which is nothing but 1 minus x square minus y square. Now, the x into y into 1 minus x square minus y square, and x into, again, the next differentiation is y. Y it is there into, it's a product of two terms. So integral of u into v you can follow. That is y, x you can put it outside as it's free from here. Here you have only, you need to differentiate with respect to, integrate with respect to only y. So x into 1 minus x square into y minus y cube is an integral. After doing this integral of y into 1 minus x square minus y square into, in terms of u into v, that is integral of uv, integral by parts, then you are going to get. Now, then wherever y is there, you need to apply the limits. The limits are from 0 to root over 1 minus x square. So the upper limit we need to apply first, that is 1 minus x square into y square. That is integral of y is nothing but y square by 2 minus y to the power of 4 by 4. So 1 minus x square into y square by 2 by minus y to the power of 4 by 4. This is what the value we got it. Okay, here what we are doing, instead of doing by parts like this, even the y term can be multiplied with each and every term. So you are going to get y into 1 minus x square. So 1 minus x square is again is again kept outside. Integral of y is y square by 2, and y into y square, that is nothing but y cube. Integral of y cube is nothing but y to the power of 4 by 4. So in this way, even the straight line linear integration can also be done here. So wherever y is there, root over 1 minus x square is there. So root over 1 minus x square, substitute the values wherever y is there. The upper limit as root over 1 minus x square, the lower limit as 0. So you are going to get this as in 1 minus 1 by 8 integral of x raises from 0 to 1 x into 2 of 1 minus x square. Wherever y is there, I'm substituting the value 1 minus x square. 1 minus x square minus 2x into 1 minus x square minus 1 minus x square whole square dx. Now, only one variable is left out from all the three integrations, three variables. We slowly, one variable by one variable, we are starting eliminating, and the last left out variable is just nothing but x. So here you can open this value. You can get it in the least form. The least form is x minus 2x cube plus x square. X minus 2x cube plus x square. Integral of x square by 2. Integral of x cube, x to the power of 4 by 4. Integral of x to the power of 5, that is x to the power of 6 by 6. So now already we have integrated, and the x limits from 0 to 1, and 0 to 1, that means wherever x is there, you can put as 1 as upper limit and 0 as a lower limit. So that comes out to be the 1 by 2, that is your x is nothing but 1 here, upper limit. So 1 minus 1 by 8, okay, 1 by 8, 1 minus 0, that is 1 square minus 0 square by 2 minus 2 by 4 into 1 to the power of 4 minus 2 to the power of 4 plus 1 to the power of 6 minus 0 to the power of 6, and here of course 0. It is not 2, it's a lower limit is 0, right? 0 to the power of 6 by 6. And upon calculating, the value is 1 by 48. So this is the how we can do the problem of in triple integrals of in Cartesian form. So let us go to another question. Evaluate integral example 2. Evaluate integral 0 to 1 and integral 0 to x, integral 0 to 1 plus x plus y, f of x comma y comma z, dx, dz, dy, dx. And he has given the function as 1. So here, in place of this function, you can replace by 1. So integral of 0 to 1, integral 0 to x, 0 to 1 plus x plus y, and the function is replaced by 1 here, 1 here into dz, dy, dx. Now, look at the limits. The limits are in the variable limits here. They are in terms of x and y, so they are the values of z. So which variable we need to integrate first? We need to integrate first with the z. Then the z variable get converted in terms of x and y. Then after that, the second limits are given in terms of 0 and x. That means they are the values for y. Because here itself at this stage, after doing the first integral, the z will be eliminated, and the remaining x and y, among x and y, as the variable limits are in terms of x, therefore the other variable which is left over is nothing but y. So these 0 and x are the limits for y itself. Suppose if in this case, at this stage, suppose y is there, then the second integration we need to do it with x, because if the variable limits are y, then they belongs to x value. So in the same way, here as it is given as x, that means that the second integral we need to do with y. Then at last the leftover integral, that is x, which is from 0 to 1. So let us see integral 0 to 1, integral 0 to x, z, that is dz, integral of dz. Integral of dz is nothing but z. Integral of dz is nothing but z. Z raises from 1 plus x plus y. So here the upper limit is 1 plus x plus y and the lower limit is 0. So double integral of 0 to 1, 0 to x, 1 plus x plus y into dy dx. Now after doing this, now integral of 1, we are doing with y. So you are going to get here y plus x is a constant. You take it outside as you are doing with y. So integral of y is nothing but integral of 1 is nothing but y plus integral of y is nothing but y square by 2. That is what we have done here. Y square by 2 into dx. Now x plus x square by 2. That means we are substituting the limits of y as upper limit as x and lower limit as 0 here. So after here the variable y is totally converted. X in x plus x square plus x square. Wherever x is there, the upper limit is x plus y. Y is nothing but x into x square into y square, that is x square by 2 into dx. So x plus 3x square by 2 into dx. And what is integral of x? Integral of x is nothing but x square by 2. And the integral of x square is nothing but x cube by 3. So 3x cube by 3. So into 3 we are going to get into 3 into 3. 3 gets cancelled here. So you are going to get this value. And x raises from 0 to 1. So wherever x is there, you put 1 by 2 plus 1 by 2. So because the lower limit is 0, so 1 by 2 plus 1 by 2, that is nothing but 1 here. So that is how we can do the integration of triple integral in the Cartesian form. Let us do one more question. Here, the third example, example 3, it's a simple example. Integral of 0 to 1, 0 to 2, 0 to 3, dz, dy, dx. As in the previous case, it is clearly given that one variable is in terms of, one limit is in terms of x and y, another is in terms of x, and another last one it is in the numerical one. So you can say that as this, the three variables are there, x, y, z, as a limit is in terms of x and y, therefore it belongs to z value. And z, when z is, once z is eliminated, the remaining x and y, the limit in terms of x, therefore they are the values of y. So like that you can conclude. But here if you go here, all the three are constant. So in this case, no, we need to find out the order of the derivation that is there inside. That is 1, this is 2, and this is 3. That means these are the values of z, and these are the values of y, and these are the values of x. So x, y, z. So if all the three are constant, we need to find out the derivation, that is the order of the derivation that is there inside the function. So integral, the function is nothing but 1 here. So you have z. Integral of dz is nothing but z, from raises from 0 to 3. 0 to 3. So integral of 0 to the integral of z raises from 0 to 3. So upper limit is 3 and lower limit is 0. So which is nothing but 3. Okay. So after 3, you can bring this 3 outside. 3 outside. Then integral of dy. Integral of dy is nothing but y. And the limits raises from 0 to 2. Again, the same version. Apply the upper limit. Upper limit is 2. So 2 minus 0, which is equal to 2. So already 3 is there. 2 into 3, 6. 6. Right? And the last leftover variable is x, and integral of dx is nothing but x, and the limits from 0 to 1, and which is equal to 1 minus 0, which is equal to 1. So already 6 is there. 6 into 1, that is nothing but 6. So remember, whenever the limits are given in terms of constants, then you follow the inside derivation that is given, the order of the derivation that is given inside. If suppose if it is in terms of variables, then you can follow the variable as a order. One by one variable can be eliminated. Let us do one more example here. Triple integral of integral 0 to 1, 0 to x, 0 to x plus y, 2x plus y minus 1 into into dz, dy, dx. And it is clear that these are the values of z, and these are the values of y, and these are the values of x. So let us start doing this problem. Now first we have to do with dz. So here z value is not there here. So what you are going to get, integral of x raises from 0 to 1, and y raises from 0 to z, 0 to x, 2x plus y minus 1 into z, and z raises from 0 to x plus y dy dz. So this is the first integral that you can do. Now you apply the upper limit. In place of z, you can have x plus y. So you are going to get this as integral of x raises from 0 to 1, and y raises from 0 to x, 2x plus y minus 1 into x plus y into dy into dx. Now the next variable that we need to do is with respect to y. So let us do this, and this can be written as 2x minus y, 2x minus y plus 2x minus 1 plus y, so that the outer bracket, it can be written as x plus y. Slowly you multiply this totally with here, so that integral becomes very easy here. So you have 2x into 2x minus 1 into x plus y plus x y plus y square. This is what we got it into dx. So integral of x raises from 0 to 1 and y raises from 0 to x. So the next variable that we need to do is with respect to y. So you're going to get it as x raises from 0 to 1, 2x minus 1 is as it is, because we are doing with y first, into dx dy. So this is the second variable that we are taking. So 2x minus 1 is constant into x, and the derivation of 1 is nothing but y plus 2x minus 1 into y. Integration of y is nothing but y square by 2 plus 2y square by 2. It is x into y square by 2 plus y cube by 3. Y cube by 3. And these are raises from 0 to x. That means wherever y is there, we need to put it as x. So if you substitute this, what you are going to get here, 2 into, this is x. This here it becomes x. And here also it becomes here x square, right? And here also it becomes x square. And this becomes x cube after applying the upper limit x. So here you're going to get it as 2x minus 1 into x, that is x square, plus 2x minus 1 into x square by 2, plus x square, one more x is there, therefore x cube by 2, plus x to the power of 3 by 3. And this only one variable is left out here, that is dx into x raises from. So here there is no need to put, because you have only one variable from 0 to 1. So the next you can write this as 2x into x square, that is x cube. So integral of 2x cube, that is 2x to the power of 4 by 4. So 2x to the power of 4 by 4 minus 2x square, 2x cube by 3 minus 2 gets cancelled, right? 2 gets cancelled, plus 2 gets cancelled, x cube, that is nothing but x to the power of 4 by 4 minus x cube, that is nothing but x square, x to the power of 3 by 2, 2 into 3, that is 6, plus x to the power of 4 by 8 plus x to the power of 4 by 12. So wherever x is there, you can put 1 as a final limit. So you're going to get it as get this as 2 by 4 minus 2 by 3 plus 1 by 4 minus 1 by 6 plus 1 by 6 plus 1 by 8 plus 1 by 12. So taking LCM, you're going to get the least form, and that will be the answer for this triple integral in 0 to 1, 0 to x, 0 to x plus y, 2x minus 2x plus y minus 1 into dz dy dx. So let us go to one more example. Here you have polar form of integration, and polar form we can see it in the next session. Let us see one more example in the Cartesian form. This is a fifth example. Evaluate integral 1 to 2 from here again a question arises, to what variable these limits belongs to. Here how many variables are there? X, y, z are there. Yeah, then the inside one, you can see that it is in terms of y and z. That means it belongs to x. Now, at this stage, the x is been eliminated. After doing the first integral, x has been eliminated. So the next option x is eliminated. So how many variables are there? Y and z. Among y and z, and these are in terms of y, so they belongs to z, and after converting, this belongs to y. So in this way you can do it. Now let us start the integration. Integral of y raises from 1 to 2, integral of y raises from 1 to 2, and z raises from y to y square. And the first integration that I can start is for x. X raises from 0 to log of natural logarithm of y plus z into e power x dx, and the rest of all you put it outside, dz dy. So integral of e power x. So here you are going to get it as z raises from y to y square, and this becomes in e power x under the limits x raises from 0 to log of y plus z, into dz. In the derivation of e power x is nothing but e power x, and integral of e power x is nothing but e power x. So you have e power x into dz dy. So here at this stage you can substitute z is equal to this upper limit and the lower limit, then everything is converted in terms of y. E power 0 is 1 into dz into dy. So integral of double integral, here double integral is there, double integral, and this the last is a numerical value, that is nothing but y is equal to 1 to 2. So double integral of y, because the triple integral in one variable we have eliminated, y to y square, y plus z plus 1 into dz into dy. The next one you can do it with respect to z. That you can write it like this: y is equal to 1 to 2, open the brackets, integral of z raises from y to y square, y plus z minus 1 into dz, close the bracket, into dy. So this wherever z is there, you can write this as yz plus z square by 2 minus z, and then to that you apply the lower limit as y and upper limit as y square. Then everything is converted in terms of y, and which upon integration you can get the numerical value, because y is the last term here, just as we have done for the previous one. We have, see, look here, we have got the numerical value. In the same way we can do here the numerical value yz plus z square minus z into from y to y square. So wherever z is there, you can replace this one. So let us see what you're going to get it as. So here integral of y raises from 1 to y raises from 1 to 2, 1 to 2, 1 to 2, integral of yz plus z square by 2 minus z into dy. yz plus z square by 2 minus z into dy, y to y square. So wherever z is there, we need to put here. So this comes out to be y is equal to 1 to 2 y into upper limit is y square. So this y square minus lower limit is y plus z square. Z square is nothing but z is nothing but y square. So you are going to get y to the power of 4 minus y square by 2 minus z, that is y square minus y into dy. It's comfortably converted in terms of single variables y. So you can write this as y into y square, that is y cube. Integral of y cube is nothing but y to the power of 4 by 4 minus y into y square. Y square, integral of y square is y to the power of 3 by 3 plus y to the power of 4 by 2, y to the power of 4 by 2, that is y to the power of 5 by 5 into 2, 5 into 2 minus y square. Integral of y square is again y cube by 3, 2 into 3, 6 minus y to the power of 3 by 3 minus y to the power of 2 by that, because the integral of y square is y to the power of 3 by 3 and y is y square by 2, raises from 1 to 2. So here you can have this as a value, and wherever y is there, you can substitute the upper limit as 2 and lower limit as 1 and get the numerical answer. Numerical answer for this. So this is how we can do the triple integrals. So remember, whenever you are doing the triple integration, if all the limits are given in the constant, then follow the derivation order of the derivation which is there inside the limit. Suppose if if any one of the limit is given in terms of variables, then you need to follow the variables in which variable the limits are given as, and apart from those two variables, you take the another variable. That means they belongs to. So that means that suppose y plus z is one of the limit, then that means that it belongs to x value, because x, y, z are the three variables there. So the integral is from y to z to y plus z. That means that they belongs to x values. So in that way, the first x has to be eliminated, and then the triple integral is converted into double integrals. Then in that again the double integral, suppose the next one is after converting in terms of z, you have, let us suppose that you have y as z to z square, y plus z. So if you have y to y square, that means that again they belongs to z value. So z has been eliminated, and third one, the y value, y is equal to 0 to 1. So like that, if the limits are given in terms of variables, then we should not follow the order. We should follow the limits, variable limits in which a variable, in terms of which variable he has given, that we need to catch hold, and slowly we can do the integrals. So this is how we can do the triple integrals of Cartesian form. In the next session, we are going to see triple integrals of a polar form, and like in the examples like this, we can see in the next session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.